1, 2, 3. Okay. You simply changed to use a kind of a bigger slide. Okay, so we mentioned we have all of these variables. We have x1, y1, x2, all of these points, sorry, x3, y3, x4, y4, and x5, y5. So for each one of these points, we create a variable. Okay? This is one particular implementation of linearization. Okay? And we create this variable. We're going to call set1, set2, set3, set4, set5. Okay? And then we're going to express both x and y as a function of these set variables. Okay, so for example, any x will be expressed as set1 x1 plus set2 x2 plus set3 x3 and that's one of the issues, that if you want to make it piecewise linear, you have to create as many points as you think are necessary to capture the nonlinear behavior of the function. Okay, but then it can grow dramatically, the number of points you are using. And then for y, similar, you use exactly the same variable, but not with x, you use it with y. But then one thing that has to happen is if you are always interpolating in a particular range. Okay, for example, your value x might be here, and your value y might be here. Okay, so in that case, the only points that matter are the points that are just next to it, set3 and set4. Okay, so these two are the only ones that should be active. All the rest should be 0. Okay, so one way to implement this is that you say that x set I is a SOS2 set, special order set number 2. Okay, set, which means that the sum of these sets, all sets, have to be equal to 1. Okay, and then if I is different than 0, then only I plus 1 or I minus 1 can be different than 0. Okay, that means that in this case, if x3 is different than 0, then only x2 set2 is different than 0 or set4, but not both. Okay. Yeah, so simply it's an additional set of, even if it looks like a lot of additional variables that you have, set 1, 2, 3, 4, 5. Okay. Essentially, almost the sum of them is going to give 1, which is going to be an additional constraint, okay, to your problem. And then you have this another constraint that it's saying that if one of them is different than 0, that only one adjacent, okay, is the adjacency condition. Okay. Okay, and then you implement such that you can, with this equation, you can actually get any number that you want, okay, if it's between the range between x1 and x2. Okay. Of course, these sets have to be set I has to be equal than 0, greater than equal than 1. Okay. Okay, but that's one approach using SOS2 variables, but there are many other approaches that you can use to to do linearization. Okay, the next point is to talk about how to handle constraints. Okay, all the methods we have discussed, we have covered so far, they're methods to find either maximum or minimum. Okay, remember that if you're finding a maximum, you can use a method to find a minimum, but simply to multiply the function by negative minus 1, by negative 1. Okay. But how to include constraints? I'm not going to discuss all methods, but simply a few methods that I think are relevant for you to get familiar with. One of them is Lagrange multipliers. And let's go back to our example where we had the gas lift, constrained gas lift optimization. Hmm? In this case, you have the objective function that was function of Q gas injected, right? It was Q oil from the reservoir, right? And this is your objective function. But now what we do is the constraint is that Q gas injection has to be smaller or equal than the Q gas total. Okay, there is a limited amount of gas that I'm able to supply. So what I create the Lagrange function. Mhm, where this Lagrange function L, that is a function of Q gas of the same variable, will be equal to um, f, the original function, minus lambda, Lagrange multiplier, multiplied by Q injection minus Q gas total. Okay, and this guy has always to be positive. Okay, sorry, this guy always have to be negative, right? This guy has to be always bigger than this one, and by putting a negative, this always going to be should be positive, right? And we are trying to maximize the function, and then we add the constraint in the objective function. Okay, so what we say is that just like we do with a regular function, we say that derivative of L with respect to Q gas injection should be equal than 0, okay, in the maximum at the maximum. Okay, is one of the conditions. In our case, we know our function is simply convex. Okay, so we can say that it will be located when that derivative is equal to 0. Okay, now we apply the derivative to this, so we get derivative of f equal, sorry, and when I derive this guy, simply what I have left is lambda, this is equal to 0, and then I have that essentially the derivative of the function okay, which is not the unconstrained case simply will tell you this number has to be 0, okay, which is what we have done before when we had no constraints, but now we have that it has to be equal to lambda. So let's say one of the subjected to okay, one of the constraints is that lambda has to be greater or equal than 0. Okay, we have the constraint that lambda times the Q gas injection minus Q gas total. Sorry, it is the opposite. Well, it doesn't really matter. Equal to 0. Okay, and the other constraint we have is that the Q gas injection has to be less or equal than Q gas total. Okay, these are the additional constraints we have. We have this one, which was the original constraint, but then we have these two that are caused by adding that variable. Okay, so we have essentially two choices. Okay, two solutions. Okay. One of them is that if lambda is equal to 0, then if lambda is equal to 0, then the derivative is equal to 0. Okay, that means that I have the optimum point will be achieved. Okay, that means that I have enough gas to, so that means that the constraint is not active. Okay, that means that I'm able to reach the point where the function is actually maximum, and in that case the constraint is no longer important anymore, this constraint, right? That means simply that Q gas injection optimum, okay, will be always less than the Q gas total. Okay, and I have, that's the first solution, and then the second solution is that lambda is positive. Okay, in the case that lambda is positive, then remember this constraint that you have Q gas total minus Q gas injection will be equal to 0. Then that means that Q gas total equal to Q gas injection. That means I'm using all the gas, okay? And also that the derivative of the function okay is not 0, but now it's lambda, which is a positive number. Okay, that means that I'm still, if I look okay at my function Q gas injection and Q oil, that means that I will be in this side of the curve. Okay, I'm going to be here because here is positive, here is 0, and then here it becomes to be negative. So if I have, let's say, the Q gas total available okay, is here, then that means that I have to be exactly at the constraint. Okay, so it's a nice way to add a constraint, a very interesting method um, to add the constraint to our original variable function. We add the constraint. Okay, we create a Lagrange function. We add the constraint. Then we derive it. Okay, we differentiate it, and then we find that we have this condition. Okay, with this lambda that we have introduced, and then we have these additional constraints. And then to this system of equations, we can have essentially solutions depending on lambda, the value of lambda. If lambda is equal to 0, then that means that this is simply essentially the first solution we had, okay, um, we simply unconstrained. The constraint is not binding, okay, it's not active. And then we have another solution where lambda is positive, and essentially then these two they have to be equal. Okay, that means that you're exactly at the constraint. And then, of course, the optimum will be when you have a positive slope. Okay, next I want to take the example when we have multiple wells. Let's wait. Okay, so now let's go to the case where we have multiple wells. So we have the Q oil now will be the sum, and here we have many, like in the first example we have made, we have two, but we have many to n, many, let's call it gas injection I, okay, well I. Okay, so essentially our total oil production is equal to the sum of the production of many n individual wells. Okay. And we have on top of that, we have the constraint that the sum of the gas rate has to be less or equal than the Q gas total. Okay, we have the sum of oil, the total oil rate is how much each well is producing, and each well has its own performance curve, okay, which it looks convex, and then we have this constraint that the total amount of gas injected, gas lift injected, it's should be less than the total. Okay, so then we use the same method. We use the Lagrange, create a Lagrange function that depends on Q gas I. Okay, it's a multivariate function, and that will be equal to um, the sum minus lambda. Okay, we have this sum exactly like what we have done in the previous case, but now the oil rate is simply the sum. It's a series of functions that they are completely independent from each other. Okay, they are separable. And here you have also the constraint. Instead of having one number, you have the sum of all these numbers. Okay, now we know that the essentially we know that uh, the maximum is achieved when the gradient of this L function is going to be equal to 0. Okay. So, and we know that happens when all each when all of the elements of the gradient are 0. Okay, so that means that the partial derivative of L with respect to I, okay, will be also 0. Okay, so and because all of them are identical, we're not identical, each one can be a different function, but it's the same, has to do it for one variable. So then we have if we derive this with respect to the I component, so we have okay, and here all the rest, all the other components that are not I, okay, here I'm deriving with respect to Okay, so all the ones that are not I, you see that there are all the others. All of them are going to be 0, and also the same thing here. So we end up with essentially the same thing. This will be 0, and that will tell you that the partial derivative of this for well I okay, and then I have to write the constraints. Okay, so one of them is that lambda is greater or equal than 0. Just make it to the left to have space. Okay, then I have the constraint that the other constraint is this guy here. Q gas total is minus, sorry, the sum. Okay. And the other constraint we have is that the Q gas total is greater or equal than the sum of Q gas injection. Okay, these are the three. So based on that, similar on the previous example, we say that two possible solutions. Okay, one of them is lambda is equal to 0. Okay, and for that then the sum of Q gas injection total of all wells has to be equal to gas total. Okay, so that means there is enough sorry, has to be less. Okay, okay, that means there is enough gas for all wells to be at their maximum. Okay, that means that this derivative of the function, sorry, this function, I should have used function I, right? Because it's a function I for each well. Function I, here I should put also function I and function I. Okay, because essentially that's can be a different function. Okay, for it's not the same function evaluated with different variable, but it's essentially can be, you can have different polynomials. Function I, okay, that means if I have enough gas, and then that guy has to be 0. Okay, so I can reach the maximum. The other solution is that lambda simply is positive. Okay, so in that case you have to use all gas is used. Okay, which means that the sum is exactly equal to gas total. But more interesting is that the derivative for all functions, here is missing the I, okay, has to be equal for all of them to a positive number. Okay, so that's the same as all wells are operating at the same gradient. Okay, all wells must operate at the same gradient. okay, for it to be optimum, which is a very typical measure we take when doing gas lift optimization. If it's constrained, all wells have to be operating at the same slope. Okay, they have to be operating at the same gradient. So even if you have, okay, one curve which is let's say very inclined and then becoming flat, okay, and you have another well which let's say is smooth and then becoming flat. Okay, you have to find a place where both slopes are the same. Okay, so this well for example might be here and this one might be here. Okay, so that's the point where the two slopes are the same of this of the well, the operating slope, if it's in the case that is constrained. Okay. Okay, now we go to another approach very quickly, and this is the last approach I will talk about handling constraint. So you have a function, let's say that it's okay, is an fx, okay, and let's say you have a function that looks something like this. Okay, maybe it goes like that. Okay, but you have a constraint, you have here a value, okay, b, and you want that x should be greater or equal than b, okay, or greater than b. Okay, one way to do it is to my original function, I want to add something that if fx plus a function called c, and this c function as a function of x should give you if x is less than b or equal than b, should be a very high value. Okay, but if x is greater than b, should be uh, almost zero. Okay, or something very close to zero. Okay, because if I sorry, not high, for example, if I want to let's say I want to minimize, okay, I want to find the minimum of fx. Okay, so then I want to be very high such that it if I go below b, then it will be a very high number, and then the function is simply looking to a minimize, okay, and it won't find any solution there. But if I'm in this range, okay, in this range where it's greater than b, then it should be zero. It shouldn't affect the original function. Okay, so a way to do it, a way to possible c x is a log. This is called a barrier function, and it's called it can be done with a log. Okay, is factor mu log and then x minus b. Okay, such that if x becomes less than b, okay, that will be a negative, and this will go to infinite. Okay, while if it's positive, then it will have a value. Okay, but then you can regulate. So this function, it tells you that. Okay, simply will go to infinity. Okay, this cx of x. Okay, in b. Okay, so every time the optimizer, if I want to use it won't, the gradient here is increasing and it's looking for minimize, so it will always tend on the opposite direction, going farther away from the from the constraint. Okay, and to avoid that this value of the logarithm itself affect the function, then this value can be a very small number. Okay, so that it will compensate, it will make it very, very small. Okay, that's it. Thank you.